So question number one is, how large will the voltage gradient generated by this potassium gradient with the open potassium channels be? Okay. The answer is that it depends on the concentration difference. The bigger the concentration difference, the more potassium wants to diffuse down its gradient, and the more positive charge has to accumulate to stop that movement. And therefore, the bigger the voltage across the membrane will be when the potassium finally stops. We calculate that voltage with the Nernst equation. It is an equation that you must memorize. It appears on boards, and it will appear on the exam, and you'll need to be able to do calculations with it. Okay? Xe is the concentration of the ion that we're talking about on the outside of the cell. Xi is the concentration of the ion that we're talking about on the inside of the cell. Z is the valence of the ion. So in the case of potassium, it would be +1. In the case of chloride, it would be -1. In the case of calcium, it would be +2. Okay? So if our potassium is 100 millimolar on the I side and 10 millimolar on the E side, this will be 0.1, this ratio. The log of 0.1 times 61 will give you minus 61 millivolts. All right? One reason why this is relevant is because the farther that the actual membrane voltage is in a real cell, the farther it is away from the potassium equilibrium potential, the more potassium will flow. This equation is called Ohm's law. You'll also have to memorize it. G is called the conductance. That is another word for permeability. Okay? Vm is the membrane voltage. Ex is the equilibrium potential. That is the potential at which our relevant ion stops moving. That would be minus 61 in this case. Okay? And the farther you get away from Ek with the membrane voltage, the more potassium will flow. I is the current generated. That's the flux of potassium. So I goes up, the bigger this difference is. Okay? That's why the equilibrium potential is relevant, because when you have an open channel, you can figure out how much of the ion is going to be flowing by figuring out what the membrane voltage is and how far away it is from the equilibrium potential. All right. I'll come back to that, don't worry. How much charge will it take to generate the voltage across the membrane? That depends upon something that we call capacitance. This is a delicate part of this lecture because I really don't want to stand up here and try to make you guys into electrophysiologists, and there's a lot of that in capacitance, and I don't think understanding it will make you better medical doctors. So what I want you to know are the things that affect capacitance and how that affects certain aspects of the propagation of the action potential that we'll go over in the next lecture. So what is capacitance? It's the number of charges needed to generate a given voltage, okay? Typically, that would be about 10 to the 8th ions to generate a 60 millivolt difference across the membrane, and that is 0.0001% of the total ions. A very small percentage, okay? So unless your cell is very small, that is going to be insignificant, because in a normal sized cell, that'll be a very small percentage of the total number of ions, okay? This is the relationship between charge moved and voltage generated. And the more charge I move across that membrane, for instance, the more potassium I move across, the more voltage I generate. The bigger the voltage difference across the membrane and the more voltage I get. I move a lot of potassium, I generate a big difference in charges across the membrane. If I don't move a lot, then it won't be a big difference in charges and the voltage won't be as much. All right? And if I want to change the membrane voltage, then I have to bring charge across that membrane. And as I bring more charge across, the voltage will go up. And it's a nice linear relationship. Okay? The slope of that relationship is what we call the capacitance of the membrane. So the capacitance is higher when you need to move more charge to generate a given voltage. So if I pick a voltage, let's say right here, and I go up and I look at membrane 1 and membrane 2, which one has the higher capacitance? Membrane 1. Very good. Because I need to move more charge to generate the same voltage. Okay? That is as much as you need to know about capacitance. Higher capacitance if you need to move more charge to generate the same voltage. And as a matter of fact, even that might be too much. Okay? I said that. So thicker membranes have lower capacitance, thinner membranes have higher capacitance. And, well, let's start with the membrane area. That's actually easier. The more membrane area you have, let's say it's a bigger cell, so you have more membrane area around the cell, then that means it has a higher capacitance because you need more charge to generate that voltage across a bigger membrane area. Okay? The ions come in, they spread out along the membrane, and I think that if you want them to spread out along the membrane, you can see that you'll need, if it's a bigger membrane, you're going to need more charge to spread out along it. Okay? So more membrane area, higher capacitance. One thing to memorize. Capacitance decreases with effective membrane thickness. That's what this figure is here. This has a lower capacitance than this membrane. Now, membrane thickness itself does not vary very much in the body. However, because your body wraps nerves in myelin, that effectively thickens the membrane, and it effectively decreases the capacitance. And what that means, as we'll soon find out in the action potential lecture, is that your action potential will propagate much quicker in a myelinated neuron, because, in part because the capacitance is much, much lower, okay? Because we've effectively made that membrane thicker, which is why this is relevant, okay? So thicker membranes, less capacitance, all right?